Hello and welcome to this video where today I want to share with you something that I've been working on for about a year now, and that is a project, a library, an environment to design and build digital hardware for FPGAs in TypeScript. Now, if none of that makes any sense to you, then don't worry, because I hope by the end of this video it will. And if it made sense to you but it was offensive somehow, then please bear with me, because I hope by the end of this video I can convince you that it's not quite as insane an idea as it sounds. Now, what we're actually going to be doing today is I'm going to introduce you to gateware-ts, which is the library and environment for building digital hardware, and we're going to look at an FPGA development board. Here I've got the icebreaker ICE40. At the moment, gateware-ts works with any of the lattice ICE40 family chips, but there's no reason that it can't very shortly support more chips. That happens to be more of a limitation of what I have on hand than anything else. And what we're going to be doing with this chip and with TypeScript is we're going to be writing a hardware driver for one of these 64 by 64 RGB LED panels. And these are typically found in big video wall displays that you would see on somewhere like Times Square. And there's many of them get put together to make a big display. But of course you can just get one panel and drive it and put some cool animations on it. And it's also a fun project. Now, I don't want to spend too much time on this in this video, because I'm going to cover it in more detail in an upcoming video very soon on this channel, where I go into what is an FPGA and how do you use gateware-ts and what are some of the real basic concepts there. But I do think it's worth just taking a moment to establish what an FPGA actually is and maybe also what it isn't. So an FPGA, or a field programmable gate array, is a chip that you can conceptually, not really, but conceptually think of as a big bag of logic gates, unconnected logic gates. And what you can do is you can design some hardware using those logic gates at a low level, so gate by gate, or a relatively high level, thinking more about registers and high level constructions. And you can design a piece of hardware, and then you can tell the FPGA to connect and arrange itself and its logic gates in such a way that it becomes that piece of hardware. And that's a configurable thing, so you can do that again and again. And it will take on new hardware configurations. Now, that's a really powerful concept, and you can build a lot of really cool and interesting things that way. What it is not is something like this. This is the Arduino Pro Mini, and on board it has an Atmel AVR microcontroller. And a microcontroller is basically a CPU, and a CPU, we're all familiar with them to some degree, and the basis of how they work, again in the kind of high-level hand-wavy way, is that it understands a certain set of operations that it can perform. It's been designed to operate on a certain set of instructions, and what it will do is every time it wants to do something useful, it will look into memory, it will get the current instruction, it will kind of work out based on that instruction and the bit pattern what it has to do, and then it will do that thing. And those things can be stuff like take this value and write it out to memory, or grab that value at that address and bring it over here. It might be something like add these two numbers together. And it could also be something more interesting like, hey, compare these two numbers, and if this one is bigger, then jump to this memory address. That is what a microcontroller is, essentially. And it's fixed, and you can't change it. So once you produce a microcontroller, and it's made of silicon, and you have it made in a factory, once you have that microcontroller, that's fixed forever. And you can't add a new instruction. You can't sort of realize that you could have done something more efficiently and change the implementation of an instruction. It sort of is how it is forever. And that's fine. That works great for a lot of things. And it is, of course, one of the world's most general purpose machines. But at the same time, it is fixed. Now, in contrast, an FPGA is completely configurable. It has a bunch of logic gates, and it's the same kinds of logic gates and transistors that the CPU is made of, but these are sort of more fluid, and we can connect them in different ways. And so you can use an FPGA to build a microcontroller or a CPU. You can invent your own CPU and just put it on an FPGA, and all of a sudden you have a hardware CPU. But obviously you can't do things the other way around. You can't make an FPGA out of a CPU. Okay, all right, I think that should about cover it. Let's move on to the panel. Okay, so here we can see both the LED panel itself and the icebreaker FPGA development board. Now, we'll talk about this shortly and take a closer look at its components, but for now, let's focus on the panel itself. You'll notice that there are 64 individual LEDs that go across and 64 LEDs that go down, giving us a grand total of 4,096 individual LEDs that all have a separate red, green, and blue channel. Now, you might notice on this particular panel, unfortunately, that there is a LED missing here and an LED missing here, and I think that was something to do with the less than fragile shipping. But it's okay, we don't need those 2 pixels. Thankfully, the panel still works without them. Okay, so how this actually works, this panel, is that we need to manipulate some electrical signals and tell it how somehow encode the red, green, and blue values for each of these individual LEDs that we need to send out. The way that we actually communicate with the panel is, if I flip it over, we'll see on the back that it's a little dark, but we'll see on the back that there are quite a lot of chips here. We have a bunch of chips down here, and we've got chips all over the board. We've got some passive components like these capacitors, but what we have is an input port and an output port. Now, we don't need to worry about the output port. That's more if we want to chain these panels together and actually make a larger screen display. So we only need to address the input signals. Now, this is a connector that we can hook up with a ribbon cable, and it has 16 individual wires, but we're only going to talk to 14 of them. And let's kind of review what those 14 signals are going to be. So bring this in here. The first and most obvious signals are going to be these R0, G0, and B0. This is us telling the panel if the red channel is on, the green channel is on, or the blue channel. These are 1-bit signals, so of course this is just on or off. And the way in which we get more colors than the 8 colors that you might imagine that you could get from such a small range is by using smart tricks and turning the panel on and off at different times to extend the color range. We're not going to worry about that today, but it is an interesting topic. Now, so we've got these red, green, and blue values. We're sending them in individually. So we have one wire for each of those. And sort of the actual general approach that we use to talk to this panel is we start on the 0th row, the first row, and we shift the bits in. And so what we're actually doing is we're starting out by giving the pixel value for this pixel, and we're sending it in down the chain as we send more and more pixels. And eventually, when we have 64 values for all of the red, green, and blue signals, we're going to want to show that line. So what we do is we tell the panel to latch those values, those 64 values at that point, and then we use this signal, BL, or the screen blanking. We manipulate this signal to actually turn the panel on this line for a particular moment. Then we're going to want to move on to the next line and do exactly the same thing. The way in which we address the different lines are using the A0 to A4 signals. So we have A0, A1, A2, A3, and A4. So we have 5 of those, and those are the address lines. And what we do is we actually think of these conceptually as being a 5-bit binary number. So we can use these signals to count up in binary to address the panel. Now, we can actually only address half of the panel in this way because 5 binary bits, only allow us to count up to 32. And the reason that this isn't actually a problem is because what we actually do is while we're sending the first row of data, we're also sending the 32nd row of data, or the row 32 and row 0. And when we're sending the first, we're sending row 33. So we actually scan the panel in this way. And the reason, of course, that it's also not a problem that we're only showing 2 lines at the same time is because the speed in which we're going to update this panel is much, much faster than the human eye can really discern. And so to a person, they'll look at such a panel that's scanning lines up and down and just see one continuous image. And this is actually the way that almost all LCD panel or old analog TV or old monitors, this is the way that it usually works. It's not that every pixel is on at exactly the same time, but rather we scan lines out individually, or in pairs, or sometimes in 4s. And different panels will have different numbers of lines on at different times. Okay, the last signal that we haven't talked about here is this CL signal, and that's the panel clock. And basically what we use that signal for is we send a pulse on that signal line to tell the panel, hey, we have a red, green, and blue value ready for you. It's ready on the electrical lines, and what it does is when it sees one of these pulses come up, it knows that it can bring that data into the panel itself. Okay, so now I think we've got an idea about how this panel works, at least from a conceptual level. Let's take a look at the FPGA board. This is the Icebreaker FPGA development board. This is an open source, open hardware development board for the Lattice ICE40 UP 5K, and open hardware is when the schematics for this whole board are available online, as are the material list for all of the things you need to put onto this board to make it work. Now, if you wanted, you could actually go and download all of those files and download the material list and send them off to a factory and have these made. And you could even sell them, and that would be completely legal. But it's much easier to just go to the 1-bit squared store and buy some for yourself. And that also supports the creator. This is such a great board, and it's designed to work with the open source FPGA toolchain. Now, open source FPGA has not been a thing for a very long time. Only really in the last 5 years has a lot of development work been done. And it's really, really impressive. And what I'm going to show you today with gateware-ts is well and truly building on the shoulders of giants. Okay, so the outputs of this FPGA, of which there are many, you can see here around the chip, there are many little lines that go out and in. A lot of those are exposed through these connectors, which are called PMODs. And PMODs are a standard in FPGA, which expose some of the signal lines and some power lines to allow you to very easily interact with the FPGA chip. Some of the other lines are broken out into these pin headers instead, and you can access them. And there are some more slightly advanced features of the board, which I definitely won't get into now on the back. You can make some solder connections on some of these pads, and you can break some of the connections to configure the board in different ways. It's all described in the schematics and the open documentation, and on the very, very helpful and very useful Discord channel from 1-bit squared. So if you're interested in buying one of these boards, I would highly recommend that. I'm not endorsed by 1-bit squared in any way. I just think this is such a great project, and I really, really love what they're doing. Okay, in order for us to talk to the panel in a little bit of an easier way, I have here an extra connector which just simplifies that. It's not completely necessary, and you could get away without it, but I've also bought this from the 1-bit squared store, and it's specifically designed to break some of these pins out in such a way that we can wire easily into the same interface that the panel uses. All right, so now we've seen the FPGA, we've seen the LED panel, we've got a rough idea of how both of those work. Let's dive into the gateware-ts code environment and see how we can actually write the hardware driver to make this work. Okay, so we're here in VS Code, And we've got a basically empty project. I've just initialized the npm. I've added the tsconfig, and I've added this file called requirements to run. I'm going to make this repository available, and I'll link that in the description. So in order for us to run gateware-ts, we need to set up our tsconfig so that it works correctly. We're using some of the slightly more advanced features of TypeScript, or not so advanced, but more modern features like big ints, and that requires us to bring in this latest version, or target the latest version of ECMAScript. Okay, we need to have installed tsnode and TypeScript, of course, in this library so that we need to build the files, but it's easiest to do that. So I'm just going to first install tsnode and TypeScript into this repository. Yeah, I actually have to tell it to install. And that's going to do its thing. And we need to have installed the FPGA toolchain. Now, I'm going to link to some resources of how to do this. It's very, very straightforward these days, but I'm not going to cover it in this video. I will cover it in the next video. So if that's already released, you can check my channel, and you should be able to find a way to do that if you're having a hard time. Okay, but the other thing we need to do is we actually need to install gateware-ts. So we just do that in the normal way, npm install gateware-ts. That will take a quick second. Okay, so now we basically have everything set up and ready to go. So I'm just going to create an index.ts file. And basically, now we can start to get into the conceptual part of how this works. So of course the FPGA, it has all of these pins, it has these output pins and these input pins, and we can actually define whether something is an input or an output on the FPGA. We have so much configurable control over it. We can define that all pins are outputs or all pins are inputs. But we're going to have to build some description of how to map those things out. And the way we do that is we build modules. So I'm going to create a class here. I'm going to call it LED Panel Demo. And it's going to extend a class called GW module, or gateware module. That comes from gateware-ts. So inside, we're already getting an error because we've declared this class and never used it. But also, this is a non-abstract class, and we actually need to implement something called a describe method. So just to stop that complaint, I'll implement a skeleton describe. In this describe method, we're going to actually describe the design of the hardware that we're going to cover, and that's going to basically come in 3 different steps. The first step is something called combinatorial or combinational logic. This is basically what you think about when you think about really basic logic gates, like taking 2 signals and you AND them together and you get a new result. You know, that happens instantaneously, or conceptually instantaneously. And it doesn't require any sort of synchronous, it doesn't require a clock, it doesn't require any other inputs than just what it gets. So that's so-called combinational logic within gateware-ts. We're also going to have synchronous logic, and that's logic that operates according to a clock signal. And the reason that we have that kind of logic is once we have clock signals and synchronous logic, we can start to build interesting things like memory and registers. And when we build hardware at this level, where it's something actually called the register transfer level. That's how it's often thought of, and that's because most of the signals that we're going to describe are going to be these registers that are able to hold a value over time and react to different changes. The third thing that we cover in the describe method is taking other modules, which are also extending GW module, and being able to wire those up to our own inputs and outputs and just reuse modules. It's a really useful concept. Okay, so the first thing we're going to want to do is we're going to want to bring in the system clock. The system clock is something that's built into the FPGA, and our module is going to receive as an input. What I'll do here is I will create something called CLK, which will stand for clock, and we'll say this is an input. And this is in TypeScript how you declare top-level members of a class so that it's known at the type level. So we're going to give an input, and it's going to be a signal definition. So we're going to create an input signal on this module. And to do that, we're going to use signal from gateware-ts. So I'll import that too. Now, signal takes a couple of arguments. It takes a width in bits. So it can be a 1-bit wide signal or a 2-bit wide signal. And when you have multiple bits, you can think of that as being multiple individual electrical lines that have the same name, or you can also think of them as binary numbers. We're able to provide assignedness, whether this signal is fundamentally should be thought of as a signed or an unsigned number, and we can provide a default value. We're not going to do any of those things because by default signals are 1-bit wide, and the default value will be 0 if they have a default value, that is. Of course, a clock doesn't have a default value, we're given it. And you might already be wondering where these names come from and where we get those from. And actually, these names are given and assigned to the pins of the FPGA in a special file called a PCF file. At least that's the case in the ICE40 architecture. Different manufacturers, unfortunately, have different standards for how this is done. And eventually, one of the goals that I have with gateware-ts is to try and standardize at least this part of the mapping into just one way. I will just copy a file that I already have around. So I'm going to bring that into this directory. I'm going to go back into the gateware-ts project itself, which has an examples folder. And in that examples folder, there is already a LED panel 64 by 64 matrix, which I've already written. And I'm just going to bring in the PCF file from there. And we can take a quick look at it and open it up and see that what we have here is we have on the right-hand side, we have the pin number. This is the real pin number of the FPGA, and this is provided in the datasheet and documentation. And we're going to set this pin number as an IO, and we're going to give it a name as clock. And it's this clock name that we're using right here. So not all of these signals are going to be used or are important. The ones that are important are here on this LEG driver pmod section. And here you can see we've got B0, G0, and R0. So these are the red, green, and blue zeros. We've got the red, green, and blue 1. And we have the address lines, the blanking signal, the latch, and the panel clock. So we have all of these signals named. We don't need to worry about which pins they're assigned to because we've defined it in this file. So now we can start describing the fact that our module is going to talk to those high-level output pins that we've defined as being related to the panel. So of course we're going to have an R0 signal. It's going to be an output this time, but it's still a signal. And we don't need to provide any defaults or anything else. We're going to repeat that 6 times for the R1, for the G0 and the G1, and for the B0 and the B1 signals. So these are all of our color signals covered. We're also going to have the address lines. So we've got A0. It's also going to be an output, and we'll also just keep it as a signal with no special values applied. We're going to have 5 of those. And we're also going to have those 3 control line signals that we talked about before. So we're going to have the latching signal, also an output. We're going to have the blanking signal, BL, and we're going to have the panel clock, which is called CL. Now, this describes fully our interface to the outside world, as well as getting our clock signal for the in. But we're going to want to have some signals which aren't going out to the outside world, aren't bringing anything in, but are purely just signals that we use within this module. Those are called internal signals. So the first simple one that we'll need is we're going to keep track of an X position of where we are in the row as we're pushing pixels out. So that will be an internal signal, internal, and yeah, of course, it's also still a signal. But this time we're going to actually alter the width because we're going to need to address 64 different pixels. So we need to have a 6-bit wide signal. And the reason is because 2 to the power 6 gives us 64. That's the number of bits we need in order to represent 64 different values. Okay, we're also going to have an address signal, which is going to be 32 bits wide. Is going to hold 32 bits values, so we're going to need a 5-bit signal. And the reason that we have this extra address and we don't just use these A0 to A4 is because it's much simpler for us to manipulate a 5-bit wide signal, since we're going to need to do things like increment it and look at different, we're going to treat it as a binary number, so we're going to do this. There's one more thing that we will need indeed, and that is a state. So if you think about it, at any given time, we're going to be doing some different things within the panel. We're going to be in a different state, and we're going to need something that is able to keep track of that, so that every time we're trying to react in a timely manner to pushing more pixels or perhaps moving to the next row, that we know what we're doing. So I'll create another internal signal. But this one, we don't know exactly how many bits we're going to need for this. So I'm going to put them into a variable called state bits, which I haven't defined yet, but I will scroll above and define now. So const state bits is going to equal, we don't know, it's going to be 1 for now. But we can think about the states that we might actually be in, and we can represent those using an enum from TypeScript. So the states that we're going to be in, well, in the beginning, we'll have a start state where we set things up, and then we're going to, at some point, we're going to be shifting pixels out, or shifting LEDs. We'll call it the shifting pixels, or shifting pixel, because we do one at a time. And for reasons that I will explain shortly, we're going to have a sort of second state that accompanies that I'll call shifting pixel off. Every now and again, we're also going to need to display the row that we've, like when we've sent out 64 pixels, we're going to display the full row. So I'm going to create a display row state. And we're also going to have an address increment state. So increment. So every now and again, when we've reached 64, we're also going to need to increment the address. So we've got now this set of states. We have 1, 2, 3, 4, 5, and to represent 5 states, we need 3 bits of information. Okay, so now let's actually think about how we're going to describe this hardware. Well, I said already that we're going to work with this address signal, but we need to somehow get like the address of these bits to be corresponding to these. We're going to do that with combinational logic. So I'm going to create a combinational logic block, and that is an array of combinational statements. So a combinational statement is essentially just an assignment of an output signal or an internal signal to some value. Okay, so we can say that this.a0 is going to get set to, and the value we're going to set it to is this.address.bit0. Now, what we're doing essentially here is just taking the 0th bit and assigning it to A0. And what I think is one of the nice features of gateware-ts is that instead of using these named methods, what we can instead do is use sort of symbolically named methods instead. So there is also an equally named method called equals. And of course we have to use this sort of TypeScript/JavaScript computed key in order to access that, and we're still calling a method, but this is kind of a nicer syntax because it sort of seems that we are actually assigning this value to this value. And I think that's something quite nice. We need to do that for all 5 of the bits. So let's do it for the 2, 3, and the 4. Okay, so this is a perfect example of combinational logic, even though it's very simple. We're basically taking one signal and splitting it up continuously forever, as long as this is running, into these 5 different signals. Now we never need to worry about these A0 to A4 signals again, and we can just continue working with the address line. Now we need to do something slightly more complicated, which is we need to look at our different states. We have these 5 different panel states, and we need to write an implementation for what we're going to do in each of these cases. Okay, so let's start out with the start state. Now, this is going to be what's called synchronous logic. So we're going to create a sync block. And in a sync block, we need to provide a signal to which we will react, to which we will be synchronous to. So that's usually a clock signal. So of course, we're going to use our clock. So every time the clock transitions from a low electrical state to a high electrical state, the FPGA is going to be able to react to that, and it's going to activate the part of the circuit which is described by this synchronous block. Now we can actually react to either the rising or the falling edge, or the so-called positive edge or the negative edge, and we're just going to react to the positive edge. Although for this case, I don't think it makes too much of a difference. Now, this is again an array of statements which are for the most part going to be assignments, but in the synchronous blocks we can actually do some slightly higher level operations as well. One of those is, for instance, to create a so-called switch statement. Now, a switch statement, as you can see here, is just a function in gateware-ts, and we're going to switch on a signal. We're going to look at the state signal, for instance. And what we're going to do is we're going to provide an array of cases. Now, I find if we're talking about switch statements in programming, or we're talking about switch statements in hardware, which are actually more likely to become something called a multiplexer, it's always good to think about what the default state is. And especially in our case, we have a 3-bit wide state signal, but we haven't actually got enough states to fill that up. So just in case any weird things happen and the FPGA somehow ends up in a state that we haven't accounted for, I'm going to create a default state. And in the default state, all we're going to do is we're going to say set the state to the panel state.start. Now the reason that we can do this with an enum, of course, is because this start actually is just going to get an automatic value of 0. And the next state, shifting pixel, is going to get a value of 1. Shifting pixel off is going to get a value of 2, and so on. It's just an incremental thing. And that's going to work out perfectly for our purposes. So actually what we're doing here is we're saying this.state is going to become 0. Now let's actually write a case for that. So I'm going to pull in the case function, and I'm going to say that in the case that we're in the start, activate this part of the circuit. So we're going to describe some kind of circuit within these bounds, and it will only be active when the start state is also active. Okay, what we really want to do here is we want to set things up, and we want to make sure that all of the signals that we are controlling are in the right kind of initial state and that nothing strange happened. So, for instance, we're going to want to set our color signals to just all be 0 in the beginning. We'll turn them all off. So we've got R1, and of course we've got G0, we've got G1, we've got B0, and we've got B1. We're also going to set the initial control of our other controlling signals. So, for instance, we're going to want to set the pixel clock or the panel clock to also be 0. Now, I actually like to think of clocks and signals which only take on the 1 and 0 values to indicate some sort of meaning. I like to think of them as low and high, or sort of like true and false. So you can bring those in from gateware-ts, and all they are is basically a signal, something called a constant, which is just a constant 1-bit 0. All right, so the clock is always going to start out at 0. The latch state, the LA, that's also going to start out as low. We don't want to latch in this beginning state. And finally, the blanking signal. Well, the blanking signal is something called active low. So as long as it is low, we are blanking. And it's kind of, you kind of have to flip this idea around if you're used to this. But in electronics and in FPGAs and electronics in general, you'll often find that some signals are so-called active low, and this blanking signal is one of those. Additionally, we're going to want to start the address out as being 0. We're going to want to start from the 0th row. Although, in truth, we could actually scan the panel out in any order we want. It just doesn't really make sense to do it in any order other than ascending. And as well as the address, we're going to want to make sure that the X position gets a value of 0, because we want to start out pushing the 0th pixel in as well. Okay, so this is now our initial state is mostly set up. So there's nothing really left to do but to assign to the next state, which is going to be panel state dot shifting pixel. We're just going to immediately start sending pixel data out. Okay, so let's create another case for that. Case panel state dot shifting pixel. And in this case, what we're going to want to do is we're going to want to assign a value to the R, G, and B lines, both of them. And I think it's kind of nice to put those together. So the B0, that's going to come up here as well. And RGB. Okay, so what I think is just a very useful beginning demo might just be to intentionally make the entire screen red, for example. So all we're going to do is assign a value of 1 to the top red position and a value of 2 to the bottom position. Actually, maybe it's a good idea to not assign a value of red to the top, but rather a value of green. And then we can see the two halves of the panel. Okay, so we're not doing anything interesting. We're not changing the values over time. We're just saying that basically every pixel in the panel is either going to be red or it's going to be green. It's not the most exciting, but I hope that this should be simple enough that we can get it working first time. Now, when we've done this, we need to also tell the panel that it can take these red, green, and blue signals and bring them into the panel. And we're going to do this with the clock, the panel clock. So at this point, we're going to want to bring the panel clock high. I need to import that. So what we're doing here is we're creating an edge that the panel can react to, very much like we are reacting to the edge of our own clock. That is how the panel also works. Okay, so we've created an edge here, and the only thing that we have left to do is to go to the next state, and the next state is going to be this panel state dot shifting pixel off. And in this state, the main reason that we have it is because we're going to want to be able to turn this clock signal low again, just so we create an instantaneous one clock cycle wide signal there. All right, so let's copy this, paste it in, and we'll say shifting pixel off. We're not going to do anything with the pixel data. All we're going to do is bring the clock to low. And now we need to basically understand, are we at the end of the row? Like, do we need to shift some more pixels, or are we sort of done here and we need to move the address forward and we need to show the whole row? As you might imagine, we can do this with an if condition. So we'll bring that in. And again, if is just a function. It actually produces a representative object called an if statement. And we'll see how this works, but basically we need to check a condition. And this is very much almost like checking truthy and falsy. We're checking if the signal be it a 1-bit wide signal or a multi-bit wide signal. If that signal is non-zero, then the following code will activate. And this is also a multiplexer. So in the case that the X position is now equal to, and I'm using equal to here with the shorthand, but we could just as well use this equal. I'll keep it as the shorthand. If it's equal to 63, which would be the very last pixel, then we're gonna activate the part of the circuit described in these array brackets. And what we're going to want to do there, of course, is we're going to want to display the row, and we're going to want to increment the address. So we'll just say this.state is going, jumped around. In that case, this.state is going to become panelState.displayRow. Now, we can actually say what we would do otherwise. So I'm going to put an else in here. And in the else case, well, we're also going to want to change state, and we're basically going to want to change to the shifting pixel state, because we haven't sent all of the pixel data we need to, right? We're not equal to 63, so let's keep shifting pixel data out. Now, after this, we can describe the part of the circuit that will increment the X counter. So we'll just simply say this.X position is going to get assigned to this.X position +1. And what this is going to do is this is going to get turned into an adder. And an adder is just a collection of logic gates that come together in a somewhat complicated way, but not too complicated, and it adds binary numbers together. And that's what this humble statement is going to turn into. So you can't think of this as being something like a programming language where this just is an instruction. This is going to become hardware. You always need to keep that in mind. And sometimes you need to also keep in mind whether you really need an adder, or whether you might want to think about building something in a slightly different way, maybe a more efficient way. And another point that's probably worth noting at this moment is that all of the statements which are contained within this array all execute at exactly the same time. Everything is happening all at the same time, because remember, this is an electrical circuit. This is a digital electronics circuit, and this is all happening in parallel. Now, the reason that we can sort of do two different things here with the X position is because this assignment is going to take a certain amount of time, and this check is going to be faster than that is going to take. And so we can actually do these things at the same time, and it won't cause a problem. Basically, anything you put inside this block within reason is all going to happen on the same clock cycle, but you can manipulate things and change things around. That also means that you can do clever things like assigning one signal to the value of the other signal, and the other signal to the value of the original signal, and that would actually constitute a swap of those two signals, and that will work in hardware, whereas that wouldn't work in software. You would need an extra temporary variable in that case. These are not variables, these are electrical signals. Everything happening here is describing an electrical piece of hardware. Good to keep in mind. Okay, so now we've got to implement the display row case. Let's do that. If panel state is equal to display row, then let's do these things. What we're going to want to do here is we're going to want to tell the panel to latch in all the values that we've just given it. So we can do that with our latch signal. We're going to bring that to a high state. And then that's pretty much the only thing we're going to want to do when we're in this state. So we're going to then move our state to be panel state dot increment address, or address increment. So this is the last state that we need to implement. And we're going to want to bring our latch signal low. And we're going to want to bring the blanking signal high. And remember, blank is actually, it's an active low signal. So by bringing it high, we're actually turning blanking off. And we're allowing the pixels to show through. Now, We also need to increment the address, of course, so let's do that. We can do that in exactly the same way that we did with the X position. So this dot address is going to become equal to this dot address. Could use plus, but again, I'll use the shorthand, +1. Now, the address line is a 5-bit wide signal, and the X position is a 6-bit wide signal. So essentially what's going to happen here is whenever this gets to 31, when we add 1 to it, we're actually just going to arrive back at 0. We're just going to roll over. That's how it's just going to overflow, because this signal only has a fixed number of bits. Same thing with the X position. We're just going to loop back to 0, and that's why we just check here. We don't do anything like set the X position back to 0. We can just rely on overflow to bring that back to 0 for us. We might not always want to do this when we're writing certain specific kinds of hardware, especially when we get a little bit more complex and we start doing things with controlling the level of brightness of each pixel to achieve more colors. But for now, this is simple enough, and this will work for us. Okay, so at this point, we've sort of got ourselves back at the right position, and we just need to start shifting pixels again. So we're going to move back to the shifting pixel state. But keep in mind here, right, that we've brought the blanking signal high here. So let's scroll back and let's make sure that when we're in the shifting pixel state, no matter what happens, the blanking signal is going to be low, because we're going to want to make sure that when we're doing this, we're not showing any pixels. Now, this means that we're actually only shining pixels for 1 clock cycle of the FPGA. And the FPGA operates pretty fast. If we don't do anything here, the FPGA is going to operate at a 12 megahertz frequency. And interestingly enough, it has hardware built into the FPGA, something called a phase lock loop, which is actually an analog piece of hardware, which does some very complicated stuff and allows you to create a much faster clock signal. So we can actually run the FPGA much faster than this. But for our purposes right now, just showing a big red and green screen, that's going to be fine at 12 megahertz. Okay, at this point we should have about covered the hardware. We've described everything we needed to do. So what we're going to do at this point is we're going to build the bit stream to actually place onto the FPGA. The way we do that is we're going to create a code generator. Now a code generator, we pull that out of gateware-ts, and what we do is we give our code generator a module. So we think of this as being the top level module. What we've written here, it doesn't have any submodules, and it is not a submodule itself, but this here is what's called a top level module. It's able to address the actual inputs and outputs of the FPGA, like the clock signal and the red, green, and blue values. So this is our top level module. So we're going to instantiate our class here, our LED panel demo, and we can give it a name. And for reasons that I won't get into here right now, we're just going to call it top for top level module. We also need to, not always, but often we're going to need to supply some options to tell the software and the FPGA toolchain how this should actually be sort of put together. So one of the things is we're going to need to point where this file is. So we can do that with the PCF path option, and we can just say it's here, icebreaker.pcf. And now this is really where the magic happens, because this next call is really, it really encompasses very many steps. But we're just going to call cg.build_bitstream. We're going to give the project a name, or the bitstream that we create is going to get a name. We're just going to call it LED panel. And this returns a promise, so you can operate on this, and you can wait for it and operate on whether it's successful or unsuccessful. And this is going to build us a binary file that we can flash onto the FPGA using the open source tools. Okay, so let's actually run this. I'm going to use tsnode because it's the simplest way. We don't have to compile all the JavaScript, all the TypeScript to JavaScript. I'll just use TypeScript. And we're just going to give it our index file. And if all goes well and I haven't made any mistakes, then it's going to go through a bunch of steps. And we can take a look at these steps. So the first thing it does is it it wrote a Verilog file. And that's sort of the core of what gateware-ts really is. It's actually a compiler for this other language called Verilog. Verilog is a very well-established hardware description language, and it's sort of like the lingua franca of open source FPGA. Now, it's not the only language out there, but it makes a pretty good compiler target, I've found. So this is what gateware-ts outputs, and this is pretty much where gateware-ts stops, and the open source tools pick up the rest of the slack. So we're going to go through a step called synthesis. Synthesis is where we take this high-level description, quote-unquote high-level description, of our hardware, and synthesis is going to turn that into much lower-level primitives. It's going to turn it into things like logic gates and lookup tables and registers, and it's basically going to unfold all that code and run it through a bunch of optimization passes, and it's going to do some analysis. And in the end, it's going to create a description of the actual resources the FPGA will use in order to make our design operate. The next step is something called place and route. So we take our synthesized design, and the place and route tool is going to basically try to understand where it should place all of these different low-level components that come out of this synthesis step on the FPGA fabric itself. I'll cover more in the next video how this sort of goes down and looks, and what the FPGA is actually made of. But fundamentally, this is a very complicated step, and some very smart people have done some really good work here to make it that the design can be analyzed and actually placed efficiently onto the FPGA itself. Now, finally, that description that comes out of the place and route needs to be turned into a binary. So we do that, we call it the bit stream, and then all the intermediate files are cleaned up, so the Verilog and everything is removed, and then we're done. And we have here this ledpanel.bin. So let's load this on to the FPGA and see if it worked. Alright, so here we've got the FPGA and the LED panel all wired together, and I've also wired in the power connection that the LED panel uses. And the first thing to do is to just take just a regular micro USB. I'm going to plug it into the icebreaker board. We can see it lines up, and we're gonna put the software, well, we're gonna put the gateware that we just wrote onto it. And to do that, we're gonna use a command called iceprog that comes with the open source toolchain. I'm gonna put this on screen as well so you can see what happens. So I'm gonna run the command now. You can see that the icebreaker has changed state a little bit. It's been flashed, and now it's ready to go. And so what we're going to do now is we're going to wire the panel in to an external power source. So I've got these two wires, and I'm just going to wire those in. They actually run off 5 volts, but they run at a higher current rate than the icebreaker board does, and so it needs to come from an external power supply. Okay, I'm going to turn the power supply on, and we're going to see if this actually worked. Okay, so the exposure level is a little bit too high to see, so I'm going to bring that down. And hopefully, as I do that, we can see that we've got half a screen of red and half a screen of blue, of green rather. So that actually seemed to have worked. And although it's not a very interesting, display that we've got here, that is a pretty positive sign, because it does mean that the gateware that we wrote first time in TypeScript worked on the FPGA. Excellent. Let's see if we can actually make this a little bit more interesting before we finish and put a pattern on screen instead. To actually make more of a pattern, we're going to need to change what we're doing here, where we draw the pixels out, and we can use the X and the Y position and combine them in some interesting way to actually create something that looks like a pattern rather than just 2 big blocks of color. Alright, one pattern that I really love that's actually really easy to generate in digital hardware is the fractal Sierpinski's triangle. It's a very famous triangle, and I'm sure you're going to recognize it when you see it. So the way we're going to do that is we're going to write some different values here. So I'm going to get rid of red, and we'll copy it over when I'm done with it. We're going to take the x position, and we're going to compare it in some way with the y position. The way we're going to compare it is with the AND operation. This is bitwise AND, like a binary AND. So we're looking at each bit of x position and each bit of the y position, and we're going to compare them. And if they both happen to be a 1, then it will stay a 1, and otherwise it will be a 0. So the y position is actually in the address line, and of course these are two different widths. So the address only counts up to 32, while the x position actually counts all the way up to 64. So what we're going to do is we're going to make the x position only 5 bits wide. There are different ways you could do this. You could AND it with just five high bits, just to isolate those first 5 bits. But the simpler way is to use slice. So we can slice from a particular bit index down to another bit index and create a smaller signal. So we're going to go down from bit 4 of x, well, the top bit of 4, down all the way to 0. And this is inclusive, so this counts 5. So we've got 5 bits now on both sides. We can perform this AND operation without any sort of strange consequences. And on the other side of this, we're simply going to say, if this happens to be equal to 0, then we're going to light up that particular pixel. And this is a great example of something you shouldn't do, and so I actually won't. I'll cut this out from here, and I'm going to come up and I'm going to create here another internal signal called Sierpinski. I think that's how you spell it. Be an internal signal, and it's going to, in the end, it's going to be 1 bit wide, so we don't actually need to fill in anything here. And in the combinational logic, I'm simply going to say that Sierpinski, if I can type it, Sierpinski is always going to be equal all the time, forever, as long as this circuit is on. It's going to be equal to this expression. The x position sliced down to 5 bits, ANDed with the address lines, and if that is 0, the whole thing will be a 1. So all we need to do now is come down to each of these assignments and write this .Sierpinski. And so what you can see is that we've only created the hardware to calculate this value one time. We create that hardware here, we assign it to a single wire, and then we reuse that wire again and again for all the different pixel values. Now, I actually noticed one bug while I was scrolling through here, and that is that here, when we were in the shifting pixel off state, we actually jumping back to the shifting pixel off state again. So we're sort of never moving from here. We should actually be going to the shifting pixel state, and that's going to allow us hopefully to actually see a pattern. It worked with the block of color, but it wouldn't work if we had a pattern. So now I can actually show you with the command line tools how this works. We're going to build the same thing before with tsnode. So called tsnode with the index.ts file. We're going to generate the Verilog and run through synthesis and play some routes, generate the bit stream, and then we can put that onto the FPGA with iceprog, and then with our generated binary file. I'm going to plug it in, and now when we run this command, we'll see that the open source tools will begin to flash that binary file onto the FPGA board itself. And now it's done, it's verified it, and it should all work. So let's take another view at the overhead camera and see if this actually works the way I think it does. Alright, so we're back here again. I've got the camera set up, and the FPGA has been flashed, and we just need to turn on the power supply to the panel to see if we've actually gotten this to work. So here we go, I'm going to turn this on, and we're way overexposed, so I'll drop the exposure down, and hopefully there we see the Sierpinski triangle. And it's worth noting here that we're actually just drawing 4 sort of 32 by 32 panels here. We're not really drawing the 64-bit panel as it should be, but it's still producing the effect. You might hear a bit of a high-pitched hum. That is the power supply working hard to turn these pixels on and off again and again to stay in the same positions. But great, that seems to work perfectly, and I think that is some more interesting imagery on the panel. If you made it this far, thanks for watching. I really hope you've enjoyed this delve into gateware-ts and into open source FPGA development in general. If you'd like to know more about this, or you're just interested, feel free to subscribe on YouTube to Low Level JavaScript. I'm going to be making some more videos about FPGA design and covering some interesting topics through the lens of hardware over there. I want to throw a big thank you out to the open source FPGA development community, for the people who maintain Yosys and NextPNR, the synthesis and place and route tools. They've done an amazing job, and they've really bootstrapped this entire thing, the reverse engineering effort, off the ground for years tirelessly, and it's amazing. I think it's one of the most amazing open source development efforts I've seen, and it's a really great community as well. If you want to try some of this stuff out yourself, I do recommend the Icebreaker board. Again, I'm not affiliated in any way with 1BitSquared. I just really like what they're doing. Also, their whole philosophical approach to open hardware. Yeah, and they're also great guys over there. So feel free to try that out. And feel free to try out gateware-ts as well. It's still very much in development. I wouldn't say it's stable or production ready by any means. But I would love to improve it, and I'm going to continue working on it. So I'll leave links in the description where you can find documentation, where you can find the repository. And feel free to reach out on the Low Level JavaScript Discord if you're having any trouble with that. You'll find other links in the description to useful FPGA topics, and I hope to see you again next time. Thanks for watching.